I'm glad that people have showed up on a relatively short notice. I can give the talk again later. Okay, so today I'm going to talk about some relatively new stuff that is extremely trivial in some senses, and a lot of it is going to be review of notation, and which will set up the result and make it presentable in a very quick and clean way. Let's see. And unlike my previous talk, absolutely everything will be well defined, and you can presumably call everything I say a theorem or a definition or something like that, and no one can complain about that. So that's nice. Good. Okay, so I'm going to talk about dualities on a lattice. This is sort of the converse of all these really nice large N dualities we've been talking about here recently. On the lattice, there are interesting dualities, and I think they do a fairly good job informing us what kind of things we can expect in the continuum, at least in certain senses. So, and there are two, I would say, main classes of lattice-like dualities that I wish to that I want to talk about here, and they're kind of related in some ways, and we will see more explicitly how the relation and how they are analogous to each other. And the two dualities are, let's see. So one is Chern-Simons-matter, which is a boson-boson duality. And it works in any dimension. And by the way, when I say lattice, I mean the spatial lattice is discrete, and time is continuous, and everything I do and say will be in the Hamiltonian formalism until near the end of the talk, where I'm going to present the Euclidean version of some of the statements I make. So on the one hand, you have the Chern-Simons-matter kind of dualities. The most famous ones are the self-duality of the quantumizing model. So also, by the way, when I write lowercase d, that means only spatial dimensions, and so when I say in d equals 1, I will mean only spatial dimensions. So so the most famous examples are the quantumizing chain duality, self-duality, and the duality between the quantumizing model in 2D to a Z2 gauge theory. And I will talk more about this later. And then the other set of dualities are things that you would call Jordan-Wigner. So this is KW, and this is JW. Yes? That's, I think historically that's correct, yes.
If you use this 2D Euclidean equivalent to 1D Hamiltonian.
Yes, that's right. Yes, yeah. So for all the Hamiltonians, I can always do the standard transfer matrix spiel and get an equivalent Euclidean action. And then I can, every duality that I say can, both sides can be Euclideanized in that way, and you can make statements about statistical models. I don't care about history in this context. So
do I understand it right if to say that Chern-Simons-matter is more natural than quantum model?
That depends on I would say that depends on your intuition and your upbringing. So yeah, I think you should be comfortable with both contexts. Okay, and so this is a duality which maps bosons to fermions, and it only really works in d equals 1. So the statement is that the quantumizing chain can be mapped, as is well known, to a model of fermions. And in particular, this is nice way to solve the Ising model at a critical point. You just map it to a theory of a single free Majorana fermion. And so this is all really well known. And then both of these dualities have avatars in the continuum case. The connection may be not necessarily well established in all cases, but I'm going to say that each of them, these are both like lattice examples of much fancier continuum dualities. And let's see. So on the side of Kramers-Venier, you can call this other ways you can call this duality in the continuum is particle vortex, where you say that the compact scalar is dual to a U1 gauge field. You can also call it, in 3D, you can call this mirror symmetry, a la interrogator-Seiberg, which is just a supersymmetric fancy version of particle vortex duality. On the other hand, this guy also has a long list of fancy continuum avatars that also work in higher dimensions. So obviously there are the standard bosonization dualities. Let's say the Sine-Gordon.
I'm really sorry.
Yes.
Please excuse me, but there are versions of this Boson in higher dimension. What's the order in between?
There are special cases, and there are very ugly versions. So I'm going to present a nice version today. And I'm going to comment on the special cases a little bit. In particular, Kitaev has a very nice case, but that only works on a honeycomb lattice, for instance. But yeah, so there and then if you are in the continuum, there are some versions here. As of course, we know of there are the Chern-Simons-matter dualities, which are also types of bosonization. You can say that this is part of the entire spiel of Seiberg dualities. And then you can, of course, add level rank. So all of these dualities seem to behave in similar ways. You take, or seem to be related by compactifications or by breaking supersymmetry, by various, by just taking the same kind of, by roughly taking the same kind of relations between operators and just putting them on different manifolds and doing different deformations. Well, I'm saying that because, for instance, you can derive level rank from it. You can go from Seiberg in 4D to give a Kutuzov in 3D, and then you can gap out all the matter, and you will get level rank. So in that sense, it's just, you can imagine starting from level rank and like adding more stuff, adding flavors and stuff like that to getting other things.
So just ask again what I think you asked. What boson to the fermion to the fermion? How do you go from that to the switch in this process?
That's good. That's good. I don't know the details yet. The four-dimensional dualities will not be something I will talk about because they will involve fancier stuff. So I'm not going to talk about 4 dimensions on a lattice here yet. So we can.
But in special cases we will. We can sort of deform it away. At least in these larger levels. In 4 dimensions? No, not in 4 dimensions. Oh, but 4 dimensions it's impossible for both of together.
Right. So there's more structure there. So so maybe I should say something like this. Yeah. There's definitely more structure and all. Yeah.
It's because the middle group, at least egonometric particles, are representations of XO3, which are discrete. In 2 dimensions, representations are representations of XO2, which is very different.
Right.
With Chern-Simons terms, we know why
right.
it would be possible, but in 4D.
Right. Yeah. That's right. That's right. So I only put this in as much as you can get the others from compactifying down to 3. So I do I can outline how this lattice procedure works in higher dimensions, and you will see that it's not nearly as nice as it is in 2 dimensions, where I will see avatars of Chern-Simons in this case.
So you have a lattice version, lattice version of Chern-Simons.
I really want to say those words, but I will not say those words yet because I'm not ready to stand behind them yet. But I really wish to say I can say why there's like tiny discrepancies I haven't resolved yet. But it's something that will behave very much like Chern-Simons in some aspects. I just won't claim that they're all the aspects there are. Okay, and the thing about these dualities, both of them, is that they tend to map local operators to local operators, or at least a big chunk of, let's say, half of the operator algebra maps to locally. For instance, in this case, fermionic bilinears map to local objects in the bosons. Individual fermions may be non-locally mapped, but all the fermion even operators will map locally. Here as well, all the local operators will map to nice, almost all the local operators will map to nice gauge-invariant operators on the other side, etc. And so that's nice. That's what you would like in a duality. You don't want something that maps really ugly non-local things to local things. In particular, well, you say something like, oh, I have epsilon d phi, and that maps to A or to F or something like that. So you can say that it needs some regularization, some smoothing, but in some sense it's local. But as I said, some operators may map non-locally, but a large number of them will map locally. Yeah, so individual. If you want the individual phi, then that will be something ugly, but the vortex formed of phi will be nice, for instance, and so on. Well, usual S duality, like electromagnetic duality, I would say it's also in this class. This is the 4D version of this. So I would say, sorry? Oh, everything I will say will be about a billion dualities, really. So I mean, I said discontinuum things. I don't know how to make lattice statements about non-abelian dualities. That's a big pitfall that I think no one has properly addressed ever. So I don't. So let me not get too committed to this.
You mean on the lattice?
Yes. Yeah. If you know how to do Kramer's-Vanier for SU2, please let me know, because I don't know how to do this.
Sorry, one more general question.
Yes.
I should know the answer to this, but you have these lattice dualities and you have related continuum dualities.
Mm-hmm.
And what is the precise relationship between them? You derive one from the other. Which way does it go?
Oh, well, it's not an easy question. It's one of those things where you need to be very careful about accessing the continuum limit, and really, if you want to really be honest about this, you have to go and do numerics to check if certain lattices have
So
nice continuum limits.
Derive the continuum duality from the lattice duality.
I would say well, it depends on your standard of what you mean by precisely, but I would probably say not arbitrarily precisely. Yeah. I think even then you would have to be careful. Yeah. For instance, if you go to self-dual points in this case, you still need to be sure that they will map to that there will be second-order transitions, etc. That you can argue, but in other cases, yeah, I don't know how to argue this nicely.
You should go on, of course, but how do you do? So let's in a lattice gauge theory,
Mm-hmm.
where you replace plaquettes by the duals, etc., etc. There isn't an abelian, non-abelian version of the duality you can do.
Not that I know in the same way.
I can't remember. Certainly the abelian case goes through, but where you in 4D you replace the plaquette with the dual plaquette.
Right.
But the non-abelian doesn't go.
Not that I know. I mean, there have been many papers written on trying to do this, and a lot of them are in the Euclidean sense, and they try to do formal manipulations with path integrals, which
That's what I had in mind.
I don't know if,
But
you have to individually assess whether they're well-defined or not. Like, for instance, there's this recent paper by Sri Raghu from Stanford on deriving these bosonization dualities in a Euclidean lattice path integral. But then again, you need to see there are statements made about how things flow and whether doubling occurs, etc. And you need to believe those statements based on intuition you got from numerics. So there's some leap of faith involved.
I'm sorry to interrupt, but
It's I don't know why you apologize. I mean, this.
And at some point we'll say time is
On the lattice, these dualities map lattice strong coupling to lattice weak. Is this right?
Typically, yes.
at least for the new ones and all.
Well, I would actually say that these dualities map. How should I say? They map at the level of algebras without ever specifying a Hamiltonian. As in, whatever Hamiltonian you specify, I can map it. So then I can presumably cook up a Hamiltonian which has all sorts of couplings where you and then it'll map to some other Hamiltonian.
Useful ones map lattice strong coupling.
That's right. The nice Young-Mills Hamiltonians or the simplest ones. Yes.
And in taking the continuum limit, you always want to be in an asymptotically free theory, for instance, or a free theory with UV. You want both sides to be at weak couplings. That's the reason why.
That certainly in 3 and higher dimensions. Yeah, that's right. Yes.
This is exactly the point. That's why I thought on the lattice it was possible to do these dualities. It may not be so useful in the continuum, which is more non-trivial. So I thought on the lattice the algebra etc. did go through them.
For the non-abelian?
But now
I
could very well be wrong.
I certainly do not know of any good example of that. Again, we can talk about. Yeah. Okay. Good. And good. So the point of the talk is to extend this guy to d equals to 2, or large d equals to 2 plus 1. That's what I'm going to talk about today, and I'm not going to do this in the naive way where you take a 2D lattice and you sort of snake through it in a line and pretend it's secretly a one-dimensional object, because that will give you horribly non-local things. I'm going to do something that works on an arbitrary triangulation. So that's why I'm going to spend some time establishing notation. And
something whose continuum limit will be the rest.
You would think, yes. In fact, when we go to Euclidean space, we will get something that looks very much like a discrete Chern-Simons-matter. But that's like in 2 hours from now. so we'll get there eventually.
11:30, the room is gone.
Oh, is that so?
That's why we had your topics.
Oh, I see. Okay. Well, the good thing is that the main point is really simple. So especially once I define the notation properly. Good. So I will be working on 2D lattice, and I will call it M. 2D. Let's say 2D triangulation. Everything I say can really be said for an arbitrary simplex, but complex, but whatever. Okay, and then I will have, and then of course I will have vertices V. And I'm sorry I'm being detailed, but it helps. It has edges E and faces F. And I will draw pictures in a bit. And then there are natural functions that you can define that live on that map vertices, edges, or faces to numbers or something. And these are, so you have chains and you have cochains. And you can call these Cn. And I will only really work with things that, so everything I do in this talk will be about Z2 systems, and I will only look at Z2 functions. So when I say Z2, I really mean 0, 1. So when I write down a function that belongs to one of these classes, and n just says whether it's 0 or 1 or 2 dimensional, then I will then these functions will only take values in 0, 1. Okay, and so that's of course these chains and cochains admit natural derivative operators, the boundaries and the derivatives, and in particular, let's say I have a one cochain. That's yeah. So these are both functions that send either vertices, edges, or faces, so 0, 1, or 2-dimensional objects to whatever field this is. And so these are going to be your scalar and 1 and 2 forms.
Why all these functions Z2 valued?
You can choose to look at different ones. I will only need Z2 valued because I will only look at Z2 systems everywhere. Yes, that's right. Okay, and then and in particular, I want to what's going to be useful for.
You said what's the code change?
So they're both functions.
Yeah.
They just have a different notion of derivative defined on them. One takes the boundary, one takes the exterior derivative. But if you don't have to worry too much about this. I mean, it's contravariant versus covariant. When you write a mu, that's the only difference. It's the same. This is a lightning review of simplicial homology and stuff like that. So.
This is the result of collaboration with couples.
Unfortunately, yes. 50% of my work was basically guessing what he meant with his notation and then working backwards to prove it. So yes, but I will keep it simple. I will not introduce higher cup products. So yes. Okay, I will also not instruct you to read papers by Milnor as I have been instructed to do. Okay, good. But this is useful. This will lighten up the notation considerably in what's to come. And every formula has an actual physical interpretation, which I will say in words. But just to record it, it's useful to do this. So if you now look at objects which live on edges, that's the one here, and take values in 0, 1. Then so on each edge you have a value at alpha of e, and then the natural derivative operator that acts on this belongs to C2, and it's defined as alpha. Let me write it like this. It lives on faces, and it's defined like this. And everything is modulo 2 because these are Z2 things. So this is the version of this is the version of taking the derivative of a form. So yeah, it gives you something that lives on a plaquette and it measures the flux through the plaquette. It measures the Wilson loop around it. So this is just useful to keep in mind. Okay, good. Physics operators. Now, I will look at various spin systems that live on these lattices. And there's a certain classes of theories that you can define. You can have spin systems, which so you can have spin systems where you have an algebra that's generated by the polymatrices. I will call them X and Z and not sigma X and sigma Z just to reduce clutter. So these are polymatrices that live on sites of a lattice. So, I apologize. Good. Yeah. Thank you. Thanks. So a spin system is a system whose algebra is generated by these two polymatrices at each link. Obviously, their products give all the other give the other polymatrix, etc. Then, if you have XE and ZE, if you have a system where you have Z2 operators living on links, then you call this the toric code. Right now it's irrelevant. I will get to that a bit later, but for now it doesn't matter.
Also, write multiplication of delta on
On a zero form? Okay, so let's see. So if you have a zero form, then it's going to be the sum of let's see. It's going to be. Oh, but there's no difference. There's no difference because it's 0, 1. So alpha plus and alpha, plus and minus are the same in Z2. That's why it doesn't matter. Yeah. Increases. This is a function on links. This is a function on faces. Yeah, that's right. Like the standard chain rule and stuff like that. Yeah, that's right. There's some lattice modifications, but roughly it does. Yes. Yes. Yeah. So all of your intuition should go through. Yeah, the details might, up to like some signs might change, but the intuition goes through. Good. So this is not a gauge theory yet. You need if you have xe, ze operators plus the constraint that the operator gv, which is defined as all the product of all the edges that contain e, if this operator is always supposed to be equal to 1. So basically, for each vertex, this operator multiplies the x's that live here. If this operator is always forced to be equal to 1, then this is what you will call a Z2 gauge theory. And this thing here is, of course, secretly dual by Kramers-Venier duality to a spin system which lives on faces. So
you're not writing sigma y for the generator that is analogous sigma x and sigma y?
that's correct, yes. So I'm just writing the generators of the algebra, and their products and sums will generate all the operators in your 2 to the n dimensional Hilbert space. That's right. Good. Well, this is not quite true, as you know. So I'm going to give a bit more details there, and then I'm going to show you how to generalize. But before I say this, before I talk about dualities in more detail, I will also give the final class of systems that I will consider, which is fermions. So a single complex fermion you can call that lives on vertices. So it has operators CV and CV dagger, which obey the usual relations. They anti-commute on different vertices. They square to 0, etc. And this is equivalent to having two Majorana fermions, which are on vertices, which I will call gamma v and gamma v prime. And then, of course, you can just define C to be gamma v plus I gamma v prime. And these operators just anti-commute. All the gammas anti-commute with each other. They square in each squares to 1. They're very simple.
So here the fermions live on the vertices.
That's right, yes. And then the dimension of this, the number of these operators is the same as the number of these operators. In particular, if you have only one vertex, if you have only one vertex, then you can identify gamma v and gamma v prime with x and z. Because x and z will anti-commute with each other. And as long as you don't have any other sites to worry about, then a single fermion is always dual to a single spin.
Are you defining a Hilbert space here?
Yeah, I mean, the Hilbert space is the thing that these guys act on, or a representation of this operator algebra that's generated by these guys in the usual way. So the Hilbert space, if there's n vertices, the Hilbert space will be 2 to the n dimensional here, and whatever the counting works, however the counting works out here. So all the Hilbert spaces are finite dimensional.
Perfect. So now the CV and CV dagger, they also act on a 2-spin.
That's correct, yes.
So the operator algebra here is basically the same as
Exactly, yeah. So this is what I said. So the operator algebra here is in fact isomorphic as this one, to this one. Both are. The only thing that you would actually want is to have a local mapping between the two algebras, because right now they're isomorphic, but there's nothing guaranteeing that there's any notion of locality. But yeah, they're both just operators of. They both generate all the matrices that act on a 2 to the n dimensional space.
And the fermions will only live on vertices?
In this talk, yes. I will. In fact, they will end up living on faces because they will be duals of something that lives on the original lattice. But yeah, like I don't need. Yeah, I do not have fermions living on links. I don't really know if that's useful to consider. I don't have any use for it here. Okay, good, excellent. And then while I'm talking about fermions, let me just remind you that that bilinears of fermions are the interesting things. So I will define the following operators. This is a fermionic hopping operator that looks like this. For an edge that contains vertices v and v prime, I can define this operator. So this is an operator which just moves a fermion along an edge. And then I have another operator, which I will call ZEF, which is also very conventionally written as -1 to the f. Sorry, this is V. This is something that counts the number of fermions at a given site. And it's equal to -I gamma V prime. So these are all the bilinears you can build out of your Majoranas, or at least certainly locally, and then you can multiply them out to get all the other bilinears. And this is the fermion number on a given site, and this is a kinetic operator. This is a hopping operator for your fermions. Here? It's not V prime. I just can't write. Yeah, it's V. Yeah. So this is only defined on a single site. This is defined on an edge. And actually, here you want to be careful about choosing orientations. Like if you want to do this properly, you will realize that this is not the same as the other way around. So there's some implicit choice of orientation when you define SE. But this is not something we need to worry about right now. I just want to introduce the notation of SE and ZV because those are going to be the operators that will map nicely under bosonization. Individual fermions will not, but these are sort of bosonic operators in some sense, and of even fermion parity, and they will map nicely. Okay, good. What is this Gauss law? Yeah. Right. This is the Gauss law. What's the question? Is that the question? Okay. Okay, good. Yeah, this is the Gauss law, and this is important because the entire point of my talk will be to modify this. So let me remind you what Kramers-Menier works like.
What kind of objects are
XE and ZE? They're still Pauli matrices. They're just defined on edges. So I want to emphasize that it's not like I'm considering a system which has all of these. I'm just saying that I can consider these different kinds of systems. They have fancy names, and they're very well understood. So these are the things you can do given a triangulation. These are the most common things one does, one considers. Okay, good. So dualities. Dualities. Okay, good. I will spend some amount of time only talking about Kramers-Menier. And I will talk about it in D equals 2. So there imagine some plane which you've nicely triangulated in some way. And there, the mapping, the nice mapping that exists is between a spin system and a gauge theory, and a Z2 gauge theory. And it works like this. So the operators that map nicely under this duality are bilinears of X. And by the way, so imagine Z is measuring whether your spin is up or down, and imagine X is flipping that spin. So XX is going to be an operator which flips two spins that share an edge. I will call this SE. So notice that was SEF, the fermionic version of this. Okay. So this operator will map to something, and then the other operator that will map will be just ZV. Okay, so these are the operators, and of course their products will all map. So these operators generate the subalgebra which maps locally. And of course, don't forget that when I talk about these mappings, this is not triangulation, is it? When I talk about these mappings, I always, the mapping will always involve mapping between the lattice and the dual lattice. And the dual lattice is, of course, just the one that you get in 2D by promoting each plaquette to a site and writing a normal like this. So if you started with a triangulation, the dual lattice will be trivalent. Every vertex will have exactly 3 lines coming out of each other, but it will not be, the faces will not be triangular. So on this dual lattice, there will be a gauge theory that's dual to this guy, and you can say that it will map like this, and this guy will map to apologies. Wilson loops on plaquettes, which are defined as this, and then E. So, by the way, so when I write this V, that means that it lives on the dual lattice. So and I don't put in any extra notation here. So when I say E and it's an operator that lives on a dual lattice, then it's the natural dual of this operator. So when I say E, that means that it's an operator that lives on the dual link that crosses this guy here. Okay, and when I say V, that's the plaquette on the dual lattice which contains this guy V. So this is a vertex on the original lattice, and it's associated with a plaquette on the dual lattice. So these objects live on this kind of, on these plaquettes, which are labeled by V. Okay?
Subscript E and V refer to the original lattice.
Yes.
V means you're in the dual.
That's right.
And then you consider the dual object.
Yes.
So an edge and edge.
Yes, and there is a one-to-one mapping between these. So this is well defined, and it's probably the easiest thing to do in terms of notation.
The left-hand side is spin system, the right-hand side is gauge.
That's correct. Sorry? Here? Well, I did, except that it's generated by a product of these guys. So so these guys are not individually gauge invariant, but but the product along a closed loop is, and that's precisely the thing that I drew there. So the point is that this indeed maps to only the gauge invariant part of this algebra.
So I was going to say that. So the gauge constraint is automatic. If you take the spin system and map it.
Exactly. Yeah, exactly. So I'm going to say this right now. So the gauge constraint, yeah.
Should I take it as an open Wilson line that has a matter Wilson line?
XE, this guy. This guy you should think of as the electric flux line. It's the thing that it's X is like the electric field. Huh? Sorry?
Is it matter, gauge field, matter?
Yeah, that's Z. So if you have this, then you will write this kind of thing, and this guy is the electric field. So this is you know, a mu psi or something like that. Yeah? Yeah, go on.
The simplest is we don't even have any matter.
Right.
We take the spin system and we map it to a gauge field without any matter. And then there is an edge.
It's AI dot.
Yeah, that's exactly. That's what I mean by E. Yes, that's right. That's right. So yeah, so imagine that this ZV is just minus 1 to the alpha E. So this is your standard gauge potential. So it's e to the I pi, this guy, if you want to think about it like that. So this is and then XC is something that shifts alpha E by alpha E plus 1.
But it's A dot in continuum.
Yeah, that's right. So XE in the continuum is A dot or is equal to the electric field. Yes.
The edge which is dual.
Yes.
Sorry.
Okay.
So if these are the two vertices V and V prime,
Yes.
this is the dual edge.
Yes.
Then it's e to the I integral A along this edge.
But
That's not true. That's not true. No.
That's not gauge invariant?
That's X. Sorry. So this what you wrote is Z. X is the other guy.
Okay,
X is the other guy. Yes.
Right.
That's right.
Sorry. Okay, that's Z. I'm
That's right,
sorry,
yeah.
that's Z.
Yeah.
That's right, so Z if you take a product.
That's right.
So maybe
That's right.
Okay, right. Has he taken the Z?
Sorry? The product of x's just means that, yeah, so are you asking how do I understand it in terms of the continuum? How do I connect it to the continuum? So it basically says that, so these are some lines that enter a given vertex. It means that I can shift, so xe, as I said, x is shifting the gauge potential by 1. So that's the only infinitesimal map you can do. And so the GV takes the lines that come out of the same vertex and shifts all of them infinitesimally. So that's like saying that a mu gets shifted by a mu plus d mu phi, where phi is only supported here. In fact, alpha e gets shifted by alpha e plus precisely that derivative of some function that's only supported on vertices. So that's the lattice version of that with that particular derivatives that I included. So yeah, so good. I mean, I'm glad I'm taking the time to explain this because the punchline will be easy once this is in place. Good, excellent. And so let me spend a bit more time on the gauge constraint across how it maps across the duality. So here I've said that so this algebra here naturally commutes with this guy. Oh, okay. So let me see. So so you see now we live on a dual lattice, and the Gauss operator is defined on vertices of the dual lattice, which are labeled by faces of the original one, and so the correct definition is this. So this is the Gauss law, and so what does this map to? What does this operator map to? Well,
all the X-rays.
Exactly. So right. Well, yeah. So basically. So here is your dual. Here are the edges of the dual lattice. They map to operators which move your boson along these. So this just maps to a product of SEs along a face. So this is just an operator which you can think takes a boson from here and just moves it along this way. And then in the end, because it's a boson, it returns to itself and nothing has happened. Or you can just plug this back in and everything squares to 0. Right. So there is this thing which you can call a vertex constraint, vertex relation, which is for matter it's something you take for granted that this is trivially something that comes from the definition, but it becomes a non-trivial constraint on this side. Okay, excellent. And of course, now you can see how this is going to work. If you have fermions, then this will not be true anymore. Because when you take a fermion around a closed loop, then this is not 1, but it's a number that depends on how many other fermions you've encountered along the way. So that means that this gauge constraint will not work. So what I will show you is that if you have a fermionic system on this side, you will again have these operators. You will just add an F and F here. But the vertex relation for fermions will also imply a gauge constraint, which will not be a standard gauge constraint. So you will get to something that is also a gauge theory, but it's a gauge theory with modified Gauss law. And the modified Gauss law, as it happens, is precisely the statement of flux attachment, as I will describe. It's defined on the faces of the original lattice, which are vertices of the dual lattice. So this F refers to face of the original lattice. Sorry, it's confusing, but yeah.
So now the product is taken on the edges that connect to this vertex?
That's right. So the product is, so this guy here is F. So this is the face of the original lattice. Yeah.
Okay.
Yeah. And so the product is either over these objects in the original lattice or over these green objects in the dual lattice. So a square becomes a star or something like that. that's the duality. All of these things are just statements of this kind of duality. Okay, good.
And whenever you say original, you mean spin system, and dual, you mean gauge.
Yeah, for in this case, yes. One has to be fluid with this.
So now with the operator, we are mapping the operator algebra.
Right.
How does it relate to actually the Hamiltonian of this?
So the Hamiltonian is just an operator in the algebra. So typically one writes, you start with a nice Hamiltonian, which is something like, SE plus H ZV. So this is just an Ising model. It just flips nearby spins, and it also weights them with some external field. And then this maps, just following whatever rules I've gotten here, to something that looks like this is XV plus H times V.
So you would never get a coupling with the most coupling.
Well, essentially, okay, so now you need to be careful what you mean by coupling, right? But yeah, so yeah, that's right. But this is essentially the Yang-Mills term. This is the magnetic term. So in the continuum, this would become a B squared, and this guy here will become an E squared. And I can write it with vectors. And so this guy here will just be their relative strength, or you can rescale these things, and this is the gauge coupling. So, and then if this is weakly coupled in one basis, then this is weakly coupled in the other, etc. Good. So basically, but yeah, I can, as I said, write down any Hamiltonian and then write down some other mapping, and I will get some result. Good.
So that's Hamiltonian A naught is
Yeah, so if you're starting with a lattice and you want to think about it as, and you want to write down a path integral, then that is automatically in the A naught equal to. Yeah, that's right. And then the A naught will essentially become the A naught field that you have to integrate over in your path integral is essentially a Lagrange multiplier that enforces the gauge constraint at each site. So at each vertex you will have to have a gauge Lagrange multiplier, and then you can imagine that Lagrange multiplier is living on a link that's perpendicular to your lattice, that's jutting out in the time direction, and that's your A naught in the path integral. And then varying with respect to A naught, of course, gives you the Gauss law, which is exactly what you want. Okay, good. And there are some important things I need to emphasize here. First, XV does not map nicely. If you're on a closed manifold, there are no boundaries, then XV actually does not map. You can only map products of XVs. So this is a statement that there's no zero mode. That's one. You basically map to a scalar theory here, but you're not allowed to flip individual spins. You're always stuck in flipping an even number of spins. So there's some kind of global mode missing, where you can't go from 0 to 1 total parity or something like that. So this
Is this related to the statement that the original model has Z2 global symmetry, while the final model does not?
Yeah, so exactly. So you need to essentially say that this global symmetry was gauged. So you're always in a single sector of the singlet sector of this gauge theory. Yes. Conversely, and this is the fancier stuff, that this model here has a one-form symmetry. That when you gauge, you get back. That's something that's visible only on things with non-trivial topology, and then we can talk about this later. How this model has to be in the gauged sector of that of that one-form symmetry. I'm not going to talk about this more. I will reflect on any questions to after the talk on this, because it's not relevant to my punchline. Good. But also, yeah, so I found this very useful for understanding all of these papers on generalized global symmetries. Everything is realizable on a lattice. Okay, excellent. And as I said, in one dimension, a similar thing happens for the Jordan-Wigner transformation. So if you imagine that we are in one dimension, and we have these two operators, then we can map them into the appropriate operators for the fermions, the ZV and the SEF. So it's the same kind of operators that map in both cases, in both Kramers-Vanier and Jordan-Wigner. It's just that we don't know how to generalize Jordan-Wigner to higher dimensions, or we didn't know. And yeah.
Even though you should probably reflect this one later, but just to ask you this question, you know, the way the mapping was done, the spin system naturally mapped to a gauge system where the gauge constraint was valid.
Yes.
But then in the gauge theory, you can free that constraint up like you do in the toric code.
Yeah.
It's not necessarily true. What's the constraint if I do the mapping the other way around? What's the constraint on the spin system side that's automatically implemented?
You can't map the toric code to a spin system.
No, you
if
can't.
that's what you meant.
You can't. But if you were so the spin system only maps to the gauge theory where the gauge constraint is true.
That's right.
Because the equations perhaps map to Bianchi identities, etc.
Mhm.
But is there conversely a constraint that the gauge, if you were to go the other way around, that is implemented on the spin side, which you can then think of freeing up on the spin
So that's roughly the story about one-form symmetries.
That's what I thought, but
Exactly. Yeah. So basically the statement was that. So that's right. Yeah. We can talk about this later. Yeah.
Putting background charges at first. That's how you relax that gauge culture.
Yeah, well, if you like, or you just say, look, here is a good Z2 theory of they use a freedom living on the links, and I won't impose this.
You won't impose it at all.
Yeah.
Or impose it at some cost, which is not used. That's the there.
Right. Yes. Good. Okay. Excellent. So, so the Jordan-Wigner transformation, as I said, works similarly. And now I can erase this part. Okay. I will proceed to just write down the explicit mapping now, without any further ado, so that everyone has time to stare at it. But the entire point is this. Okay, so there's some extra stuff needed to understand the mapping, to write down nicely the mapping between a fermionic system and the corresponding gauge theory. And by the way, from now on, so let's call this Jordan-Wigner in 2D. And I will always, and fermions will be on the dual lattice, which I will call MV. And the gauge theory will be on M. So when I write things like ZF, that will be defined on the faces of the original lattice, or on the vertices of the dual lattice. Okay, and the operators here will be SF. And here I will have, again, operators that are XE and ZE plus some gauge constraint.
So the fermions live on the vertices of the original lattice?
No, the fermions live on the dual lattice, on
on the vertices
of dual lattice.
vertices, right?
On vertices of the dual lattice,
Okay.
which is the same as faces of original.
Okay.
So fermions live on faces, and the gauge theory lives on what I call the original triangulated lattice.
And F always refers to fermion.
That's right. Yeah. F in the superscript always refers to fermion, and in this case it means that it's on the dual lattice. Good. So this counts the number of fermions, the fermion number at each face, or site of the dual lattice, and this counts and this moves. So obviously, if you have a fermion here, and you have an operator defined here that just moves your fermion across here. That's just moving it across along this link on the dual lattice.
And that's what SE does?
Yes, that's right. That's right. Good. So to define this gauge constraint, I can tell you immediately what it's going to contain. The gauge constraint will instead of looking like GV equals to 1, the gauge constraint will become something that looks like GV times some appropriate product of F's that depend on V is equal to 1, of these guys is equal to 1. And I will need some more machinery to explain what this guy is. But roughly, this means that if you have a lattice and you have some site, then the charge on this site is not just is not determined by just what's the electric flux flowing into it. So these x's calculate the electric flux that flows into your given site, and by the standard Gauss law, it has to be equal to 1. This guy says that the charge on this site is equal to the number of the electric flux flowing in plus the contribution from some charge which is attached to some of the plaquettes. Basically, if there's non-trivial magnetic flux through this plaquette, then there's immediately an extra charge associated to this vertex. To define this properly, you need a canonical association of vertices to faces. So that's what I'm going to talk about next. That's the thing that is not very well known in physics, even though in some parts of mathematics, this is a well-known property of lattices, or like a well-known thing that you can do on lattices. And of course, in the continuum, this becomes the spin structure.
Only one face. That's Wn.
No, it can be the product. This is the product over all f's that satisfy some relation that I will explain now.
So not the phases that go around the world.
Not all, some.
That's what I was going to ask. That's the other natural choice.
It's
Some, it's very strange.
It's yeah. So yeah. Okay. So excellent. So the yeah.
This is not implementing that divergence of E equal to 0.
This guy.
Yeah.
This guy is so okay. So this guy here was implementing that the divergence of E is equal to rho, which is equal to 0.
Yeah. Now I have to.
This is divergence of E plus the flux plus how would I call this? Yeah, now you would say that the Gauss law says that you now have an extra, well, let me not call it K, or something like this,
He's saying it's some discrete version of Chern-Simons.
It is, yeah.
So rho is like.
Yeah. It essentially says that rho is equal to K times F, if you want, or I think that I got this right.
Wait, but this, what is wrong there? There's no matter, right?
There's no matter, so, yeah, so I'm just saying that then a magnetic flux will just create the electric charge in the same theory. That's right.
Maxwell cluster.
That's right. That's right.
But somehow not in all faces around the world.
Yeah, so that's determined by your choice, by essentially a discrete choice of spin structure, how to associate faces to vertices. And I will talk about this now. So, and this is why it's useful to think about triangulations, because that's where it's actually simplest to explain. So I will introduce the concept of a branching structure. Which is also called Castelline structure. And as I discussed it, I mean, this is something that people in statistical physics and integrable systems know from the 60s.
And there's no free parameter between. It's just, there's nothing like the analog K.
So this is a Z2 theory, so K can only be 1 or 0. If it's a Zn theory, then you can have W to some other power. So this is not something that's been worked out yet, by the way. This is something that I have high hopes in understanding better in the future. Good. So this is a choice of orientations of the links on the lattice that satisfies the following constraint. So here are some triangles. You have a branching structure on the lattice if your orientations are chosen in such a way that no triangle has all links going in the same direction. So writing it in the other way is not allowed, because then this triangle would have everything going in this direction. So then you can have, you have things like this. So again, I'm not allowed to, I have to put this like this. And in 2 dimensions, it's always possible to assign such orientations.
So every face, the arrows are such that they both align.
That's right, yeah. In higher dimensions, this is not obvious, and if you cannot assign this, then there's no mapping. There's no consistent mapping.
But it's also no matter what manifold is calculation. But I
Ye-
want genus.
Yeah, so I saw some math papers which say that you need an even number of vertices, but that's clearly that's clearly not true, because if I take just a single face, that's it has an odd number of vertices, but still certainly I can do this. So there's some caveats. I think there might be some very global constraint of that, some Z2 kind of constraint, which I don't understand completely yet. But let's assume that we are doing it in a case where it works. Any lattice you care to write down immediately will work. Good. Excellent. And of course, notice that if you flip the orientations around that of all the edges that emerge from a given site, you still get an admissible structure. So that means that the set of sort of topologically distinct structures that you can put in is sort of like it just depends on the genus of the surface you're on. So you see, basically you can classify all possible structures, but just by flipping these local things and specifying how they move around cycles on your lattice, if there are any cycles.
But is it that to flip the arrows attaching one vertex, you get different branches?
No. You get another admissible branching structure.
Yeah, the branches.
That's not the same as spin structure. Spin structure, yeah.
I see. Yeah, branching structure.
Yes.
But now you say that so there are roughly as many as the genus.
Topologically distinct ones, the ones that you cannot get to from one to another by just flipping these, by locally flipping. Yeah, that's something. Yeah, that's right. That's right. Yeah. Which is just the Hilbert space of Wilson loops along your cycles. Anyway, okay, good. Let me not. Okay, so this is, and why this is useful is that for each face, now you can canonically label distinct vertices. So there's going to be only one vertex which has two lines coming out, looking at just this face. And you will call this vertex and label it 1. Label this guy 0, 1, and 2. So basically, this branching structure determines a map to these vertices f0, f1, and f2. Okay, so there's so for every f, there's a specific f0 that I know. Of course, a single vertex can be the f0 of several different faces. So for instance, this guy.
So F0 is a point.
F0 is a point. Yes, that's right. So F0. Yeah, I guess these guys are in just sites, vertices. So this is a face, and it's canonically, from a given face, you have a canonic labeling of the faces and of the edges. Of course, now you have, I have 0, 1, which is a particular edge. And now, this guy here.
Sorry, I didn't understand that.
Yeah.
So I understand there's one, on this face, there is one vertex where two lines are outward directed.
That's
and
right.
all the other vertices is one in, one out.
That's right.
And then what was
Uh,
this? F0?
One of the
One
other
vertex.
one is one out.
Yeah, and
One
the other one is
is
in. Yeah.
Oh, two in.
Yes.
Zero is the guy with both out. One is the guy with one and one out.
Oh.
Two is the guy with
And for each face, I separately label them. Yeah, that's right.
Okay.
In general, you take the longest path and you follow the arrow and label the vertices along that path.
I don't.
Higher than
I don't know that. I don't know about higher dimensions. I don't know what's the useful way to generalize this in higher dimensions. There is a generalization, but let's not talk about that. Okay. What I do want to say is what this precisely means.
Again, if I did a gauge transformation on the vertex 2, it
Yes.
would make the two ingoings two outgoings, right?
Yes.
So in that sense, I can flip your labels around.
That's
for
right.
local gauge
That's right. So there's a choice that's necessary.
Gauge
It's not a gauge transformation on the fields. It's just a choice. Yeah, exactly.
A transformation of branching structure.
Yeah,
These are labels that have nothing to do with the gauge.
that's right.
It has nothing to do with
This is something that only is like a labeling of.
Sorry,
Yeah.
sorry, just come again.
So this is the extra bookkeeping on the lattice that you need to do if you want to account for fermions,
Okay, sorry.
which is very similar to what you expect in the continuum.
So here, fixed is
if I have time, which I might not, but yes, yeah, okay. Yeah, so let's see if I can get there. The point is that more precisely, the new gauge law that has to be obeyed is that GV times the product over all f's such that V is equal to F0 of the WF is equal to 1. And this means that this is essentially saying that if you have a magnetic flux coming through here, that means that this guy here has a free charge dangling at the zeroth vertex of that face. That's the W is the Wilson loop operator that around that plaquette.
So you take all faces such that what is it?
Such that this vertex is the anchor, is this zeroth vertex.
Okay,
So here I would do a product of the Wilson loop here and the Wilson loop here. That is the choice.
Does the fermionic theory depend on your choice of branching structure?
There is a choice of no. The answer is no. There is a choice of orientations that you need to do in the fermionic theory, but then you can absorb
So your condition
yeah.
here seems to depend on the choice of branching.
Good. So the map will be. So what's going to happen is that the map will be something that looks like this. So ZF, the number of fermions will map just to these guys. So the magnetic flux will map to the fermion number, and this guy will map to some will map to this. Will map to the electric flux operator times Z2 valued function of the edges, which is only determined by the lattice. So your bosonization, once you choose the branching structure, it induces the correct bosonization along these lines.
Yes, so the fermionic theory is independent of branching structure, but the map depends on
That's right.
branching
That's
structure,
right. That's
and
right.
Therefore, the condition.
That's right. Yeah. Yeah. So that's how I would phrase it. Yes.
So there are many possible duals of the fermion.
There are many choices. Yeah. There are many choices, but they're all. Yeah. Now you can wonder whether this choice is useful for. I mean, these choices are really different in some sense. That's right. So as you go around the cycle, the fermions. So if you consider this, so you go around a face that's sorry, no, it's this one. So yeah, so this is like if you take a so you're talking about a non-contractible cycle. Then you will get then you will get some non-trivial number, which will then tell you what the spin structure is.
So is that in one-to-one correspondence with the choice of branching structure?
I wouldn't say one-to-one. It's like many-to-one or something like that. In many of these choices will correspond to the same cycle of the fermions.
It probably be different equivalent class.
Yeah, that's exactly right. Yeah, that's what I want to say. Yeah.
So when you say branching structure, you mean just one choice branch?
Exactly. Yes, that's
Not
right.
the equivalence class.
Yeah, that's right. That's right.
So
I don't know if that's. I mean, that's how we always used it in the paper. I don't know if that's the mathematically standard nomenclature, but yeah. So in particular, if you now look at fermions that move along a closed loop in the dual lattice, then you will see that this guy has to be proportional to some Z2 number times.
That confused me.
Yeah.
Fermions live on the original lattice or the
On the dual lattice.
This is the gauge theory lattice.
That's right. That's right.
I didn't quite understand the appearance of the branching structure in the map. What is the
The eta E is a number that you can determine by consistency relations, by consistency relations that are like this. By requiring it at every vertex and for every loop, then taking the fermion around in the fermionic theory is the same as taking you need to get something that's equivalent to the gauge constraint. So there in the fermion theory, what I wanted to say is that in the fermion theory, if you take a fermion around the loop, you will get some Z2 number times times some product of the fermion numbers along the way, as I said. And so these guys will map to W's, to some W's. These guys will map to some X's. Actually, these guys will just map to GB. So you see, GV times W has to be equal to whatever number you get here under this map. So you just demand it for every loop. You can do this consistently.
Probably it only depends on how many edges there are on your base.
Depends.
Because you get psi. That whole structure basically
It
determined by how many edges.
Well, not just, well, I would say not just how many. Oh, okay, this is partly controlled by this number here, yes. So this number here will be some counting again of the number of links, of certain types of links of certain orientation that come out of your lattice.
That would be stochastic.
No, that's okay. Are they trying to get us out? Well, I did show you the main punchline. The only thing that I can say in the next minute is that if you do this,
I really could stop it. Just very quickly. All right, go ahead. Ask you later.
Yeah.
We can take the tea.
No,
Yeah.
sure.
So the entire point is that if you now do the standard transfer matrix method to get the Euclidean description of the thermal partition function, let's say, to find the path integral or the lattice path integral that's associated to this guy, you will actually get something that looks like a discrete type of gauge theory. To write this down, I need to introduce the notion of cup products, which are sort of instead of the wedges that you have, when you write A wedge dA, you have the discrete analog is this thing called the cup product, and then you get something that looks like A cup delta A, where delta is this differential operator that I told you about. So it looks it's not quite Chern-Simons because the prefactors don't match and so on, but in the continuum you can imagine it's conceivably going to be Chern-Simons. And that's interesting. So I can stop with this, and then obviously I can continue later when we have time to talk. So thank you.